All right, welcome back. We're going to resume where we left off. We're going to start talking about inclusive probability. Let's talk about that and a few other concepts today. And we're just kind of running through tools we have and things in our probability tool belts and things we can ask you about. So here's one that we haven't come out like a lot and said yet, but we might want to ask you about the probability of one event happening or another event. That is, what's the probability of getting a Frosty or a burger when you go, right? And this formula, it's called the inclusion-exclusion formula, is the way of computing that probability. But it should make sense. It's not a formula. I mean, it's a formula I suppose we'll memorize. But it shouldn't be one that you really have to think hard about to memorize. If I ever if I were ever to forget this formula, if I were to forget it, I would just think about the Venn diagram. The picture of this should make good sense from our original Venn diagram picture. So I guess I don't have a picture of this coming up. I thought maybe I had an animation that had this come up. But all right, so we have A and B. The probability of A is this. The probability of B is, let's get another color. The probability of B is this. And if we add those together, we get the probability of the combined area. Oh, wait, except when we add those together, we've counted this middle section twice. And so to account for that, that double counting, so we've counted this in yellow, and we've counted this part in white, unfortunately, and then we've counted this middle part. We've ended up counting this middle part here twice. And so we need to subtract one copy of that middle football area. And that is, in fact, all this formula is saying, right? Do you see it now? I hope you see it, and I hope you don't think of it as something that like you have to labor to memorize. It should just kind of make sense from the geometry of the Venn diagram. Okay, that being said, and this is maybe, this particular approach might be a little bit overkill for this particular problem, but let's just show you that it works, because I think the answer to this is pretty intuitive, but let's show you that how this might operate. What is the probability of drawing a heart or a jack from a standard deck? We draw one card, that is, and what's the probability that it is either a heart or a jack? Okay, so probability of getting a jack or a heart is equal to the probability of getting just a jack plus the probability of getting a heart minus the probability of getting both. And before we even begin this problem, you might want to think, is it possible to get both? And then you'll answer to yourself right away, oh, right. There is one card we could pull, that with only one card being pulled, we get both simultaneously, a jack and a heart. And that is, of course, the jack of hearts, right? So there is a possibility of that happening. What would this formula say if the two events were what we would call, you've heard this language before, what if the two events were mutually exclusive? That is, one, what's the probability of drawing a heart or a spade? Well, then you wouldn't have this piece at the end here. It would just, or you would, it's just the size of that intersection would be 0, and so the formula still holds even in the case where we have two events that are mutually exclusive. This formula still holds. All right, so now let's compute each of those. The probability of a jack is 4 out of 52, and I think I'll keep the 52 in the denominator, even though you're tempted to reduce that to 1/13, I'm sure. And the probability of getting a heart, well, how many hearts are there? There are 13 hearts, there are 13 of each suit in the deck out of 52. And how many cards are there out of the 52 that are a jack and a heart simultaneously? Well, we identified it already. There's one card that is both simultaneously a heart and a jack. All right, and then this gives us, and again, I think this will confirm your intuition. This will give us our final result of, well, what is that? 4 plus 13 is 17, minus 1 is 16 out of 52. If you care to reduce that, I guess you can. You could say that's 4 out of 13. Right? So that's what we mean by inclusive probability, this kind of idea that is it true that two events can happen simultaneously? And we'll practice that some more soon. All right, so here's another one that might be, well, maybe, just maybe, could be approached using a similar technique. Let's take a minute to read the question first. It says, after Hurricane Katrina relief, 200 people were surveyed in a community, and here are the results. 65 said they donated food, 50 donated money, and 30 said they donated both. So we understand there to be some overlap, right? And that there were just check boxes on the survey, and okay. A newspaper wants to figure the percentage of the people in the community who donated something at all, that is, altogether. What percent of the people surveyed donated something? So is this a case where we can use the previous formula? Sure. This is the probability of someone donating food, or money is the thing we want to compute. That is the group of people who donated food, who said 65 total people donated food. That includes some overlap with the people who said they donated money, right? There are some people that are in both of those groups that are included in those numbers. So this is the probability of food plus the probability of money minus the probability of both, right? Because we're counting it twice in the previous two terms of this calculation, right? That's the football analogy. All right, so what are those things? That's 65. How many total people is it? 200? This is 65 out of 200 plus 50 out of 200 minus the intersection and all of these things. This is a nice one, right? As soon as you understand what kind of thing I'm asking for here, I think it's pretty clear. It's pretty clear that I've just basically given you all of those answers just straight out in the problem. That's kind of nice once you understand the approach. All right, and then what does that come out to? Well, I don't know. Let's see here. That's 65. 65 and 20 is 85. Is that right? Someone check me on that. 85 out of 200, which is equal to 42.5%. Is that right? 42.5%. 65. 42.5% is. I mean, you could leave it the way it was, I guess, right? What did it say? Oh no, actually that's the actual answer to this question. It said it wanted percentage. So let's not leave it this way, actually. Ordinarily, if it didn't ask that, it'd be fine, but it does ask for the percentage, so let's give it 42.5%. Exactly, not rounded, but 42%, 42.5% exactly. Good. So I hope you see why this inclusion, I don't have much more to say about this idea. We do have some interesting problems for you to take a look at, and see how that goes for you. All right, we're going to switch gears a little bit. The last piece is going to be enough for you to get through the packet that I gave you. I think you're going to be well prepared to do some of that. So let's switch gears a little bit. And actually, I'm going to return all the way back to our first day when we were talking about probability mass functions and probability distribution functions. And I want to just throw a couple extra problems at you. We want to do a little more with that. We had to at least say something about those things, that idea of a probability distribution, because it's hard to get off the ground in probability if you don't have that kind of as your basis. So let's do some other interesting problems that involve that. Like I said, we're switching gears just a little bit here. Okay, so let's take a look. We have some random variable, and it can take on only the values 0, 1, and 2. The problem doesn't clearly say that, but let's assume that that's what it means. It can only take on the values 0, 1, and 2 with these probabilities, alpha, 2 alpha, and 3 alpha, respectively. So what is the value of alpha then? Well, if this really is a probability distribution function, then what should be true about those 3 probabilities? Yes, I hear you say the probabilities should add up to 1, exactly. And when we add those up, we get 6 alpha equals 1. So what's alpha? You got it. It's 1/6. Call it a day. And pack up. All right. Anything else we should say about that? I think that's pretty simple. I just want to make sure you're okay when this question comes at you, that you're okay, right? It's not terrible, but they can be interesting, right? Like, there's one that maybe is more interesting. I don't know. Let's take a look. All right. So here we've got a probability mass function with support 1, 2, 3, 4, 5, 6. There it is. And then we've got this function, the mass function given right here as k over x. Well, what is k? Let's figure it out. Well, what should be true about these? Well, it should be true that k over 1 plus k over 2 plus k over 3, these are the probabilities of each of these things happening, k over 4 plus k over 5 plus k over 6 equals 1. And oh boy, why did you do this to us, Mr. Chase? Oh, this will be fun though. We just have to multiply this equation through all the way by the least common denominator. Oh, great, wonderful. This sounds like a good time. Okay, what is the least common denominator here? How about, well, we need a 2 and a 3 and a 5 and another 2. So what is that? We need to multiply through by 60, maybe? Is 60, I think 60 is what we have to use. Okay, so I'm going to multiply through this equation by 60. We get 60k plus 30k plus, just to clear all the fractions, plus 20k plus 15k plus 12k plus 10k equals 60. I multiplied all the way through by 60. All right, are we having fun yet? So this is, I mean, I think we understand how to do this problem, but it's a little bit of a pain maybe. So what do we get on the left here? 60 plus 30 is 90, 110, 125, 137, 147k. All right, so this one doesn't work out so nicely. K is, are you ready? 60 over 147. All right, it said find in part A, find the value of k. So there we go, we did it. So we now know that our probability mass function is actually, k is no longer unknown. Probability that big X equals little x is equal to 60 over 147x. Is it okay if I write it that way? Okay. All right, so now let's do B. What is the probability of x being 3, 4, or 5? Do we interpret that correctly, right? So that'll be 60 over 147 times 3 plus 60 over 147 times 4 plus 60 over 147 times 5, which is, I don't know. Let's see here. We can just do 60 over 147 times 1/3 plus 1/4 plus 1/5 as well. One way or another, please get this answer here. I'm getting 47 over 147, which is approximately 32%, approximately 32.0%. Yeah, whatever. 47 out of 147 is a good answer there. So how's this look? I think we like this. Sounds good to me. Yeah. All right. Let's keep moving. So the point is, we can ask more interesting questions. I think that's the point. All right. So more questions like that will come at you. I think there's some in the homework associated with this that include some crazy stuff. You might have to set up a system of equations and solve for 2 different interesting variables. They can throw different things at you. All of them come with that same premise, though, that the probability distribution has to add up to 1 and all that. Okay, let's turn our attention now to the idea of finding the mean value of a distribution. So take a look at this. What is this even? Sorry, pardon the pun. What does this even mean? Huh? Well, yeah, what does it mean to find the average value of this distribution? Okay, well, here's one way to think about it. If the probability, first of all, I hope everyone understands the way I've depicted this probability distribution, right? This is the different values we can have are 1, 2, and 3, 1, 2, 3, and 4, and they come along with these probabilities. Right? This is like calculating your GPA or rather maybe actually your grade in this class with different weights in the category, right? Homework is worth 10%, something, projects are worth 20%, quizzes 30%, and tests 40%. Is that actually our breakdown? I think it's not actually, right? It's 50% tests, but whatever. How would you compute that weighted average, okay? Or you could think about there are, 10 marbles in the bag. One of them has the number 1 on it. 2 of them have the number 2. 3 have the number 3, and 4 have the number 4 on them. Right? So whatever. What is the average value of all of those numbers? Right? So there's a couple ways you could conceptualize it. So in the end, though, how do you calculate your weighted average? Well, you multiply these together, right? 1/10 times 1 plus 2/10 times 2 plus 3/10 times 3 plus 4/10 times 4. And you could if we conceptualize this as being marbles in a bag or whatever, like I said, a ball like that have these numbers written on them, then how would you conceptualize it that way? Well, there'd be one that has their total of 10 balls, or 10 marbles, one with a number 1 on it. There are 2 that have the number 2 on it, so we have a 2 plus a 2. And then there are 3 that have a 3. And then there are 4 that have a 4. And instead of writing, that, and there are 10 total, right? Instead of writing that, you might have written instead 1 plus 2 times 2 plus 3 times, there are 3 3s and 4 4s, right? Anyway, the point is, don't you see, I hope you see, that this is the same calculation as we just did down below. It's the weighted average. I don't know if you're comfortable with that, whatever. Okay, and what do we get here for this particular one? Well, we get, it's all over 10. We'll get 1 plus 4 plus 9 plus 16, right? 1 plus 4 plus 9 plus 16, which is 30 over 10, which is 3. All right, so wait, this is a probability? No, we didn't just calculate a probability. We just calculated the average value, or the mean value of our random variable x. If we were to keep pulling, if we were to pull a marble out and write down what you got and put it back into the bag, and you were to keep doing this and put the marble in, take it out, and you do this randomly for 1,000 times, we'd expect on the long run that on average you would get a ball or a marble with the value 3 on average on it if you were to write all of those values down and in the end average them, right? This is also called, instead of the mean value, those stat people in the room probably know, it's also called the expected value. All right, so I wanted to do it once up here as an example. We've done this a bunch of times because the intuition is stronger. I don't want you to be scared by all this nastiness, okay? This is in fact what we just did, and if you're not comfortable with the summation notation stuff here, don't worry about it. You can just write this stuff down at the bottom down. The whole point is, in the end, it's just the probability times the value plus the probability times the value. You do that, add them all up for all the values, right? Just what we did right here. All right, so in fact what we just computed up here is the expected value of our random variable x. Yay! Good job, everybody. Okay. So are you okay with the language here? It makes sense because I think expected value is a good name for it. It's what we expect in the long run. Now, our first example was maybe a bad one up here because we got 3. Is it possible for this average to come out to 3.1 or something? Absolutely, and you guys know that with your grades. Is it possible that your grade, your average, your GPA comes out to 3.84 or something like that? Absolutely, it can come out to that. Does that mean that you can get that as an actual grade in one of your classes? No, right? Likewise, if we were pulling marbles out of the bag that had numbers on them, if you got the average was a 3.4 or something like that, does that mean you'd ever actually pull a marble out that had the number 3.4 on it? No, not at all. So the expected value is the long run average, right? If you were to do this millions of times, what would on average you get? And so the fact that that could be a decimal does not bother us at all. Just like when we say the expected number of children in an American household is 1.2 or something. That doesn't mean when you go to a house and open the door, you expect to see on average 1.2. Well, you expect to see 1.2 kids. That doesn't even make sense, but it does. That's still a meaningful stat to you, isn't it? Right? You've heard that kind of thing before. I think it's actually maybe lower than that now these days. I don't know what it is. Anyway, but the point is, if you were to continually survey, the long run average would be 1.2 kids in the family. Okay, I just want to make sure because people will get confused by that idea. Expected value is the expected long run average, if you want to say it that way. All right, so let's take a look at these two examples that deal with this idea of expected value. Okay, maybe it's not obvious at first that they do, but they do. Okay. Take a look. The first prize for raffle is $4,000 with a probability of 0.001. And the second prize is $1,000, the probability of 0.003. What's a fair price to pay for a single ticket in this raffle? Okay, well, my question is, what are your expected returns from playing in this raffle? Well, we get $4,000, don't we? But we only get that with probability 0.001. And we get $1,000, but we only get that with probability 0.003, a little more often. And so what are our expected returns in this raffle? That's the question. Well, 4,000 times 0.001 is just 4. Hey, that's easy. And 1,000 times 0.003 is 3. So our expected returns are 7. What are we talking about here? Oh yeah, this is units of dollars, right? $7. All right, so this is not actually a bad raffle. Now, this is not the only consideration you would make, but what I would think is a fair price, and by fair price we mean we have like a zero-sum game, right? Like that it's fair both for me and the person running the auction, right? So the person playing and for the person that on average we come out to $0, right? Like if we were playing this for the rest of our lives every second, in the end, neither of us would be at a loss, right? Both of us would still have a balance of same amount we started with. So I think a fair price to pay would be $7, right? If I paid $7, then my expected returns are $7. In the long run, I'll have earned, well, I'll have nothing, right? In the long run, that's what it would mean to be fair. Okay, so this kind of conceptualizes that idea in a slightly different way, but it's still the same idea, right? So here's an auction, another lottery of some kind. It looks like, just the way that this is set up here in this table, it looks like the ticket price was $5. You see that? That's not a mistake. That's negative $5, right? So if you pay for the ticket, your expected returns often are, in the end of the day, you're down $5. But occasionally, you win $200. So does that make sense why your net return would be $195, right? So at the end of the day, you paid $5 and you got $200. So you have netted $195. So does that make sense? I think that's maybe the theory behind this. You don't have to actually understand that, though, to do this problem. First of all, of course, the value of Q must be, because this is a probability distribution, 999 out of 1,000. I don't have more to say about that. But then what are the expected winnings for someone entering this lottery? What on average happens, right? Normally it looks like, a lot of the time you go away with a negative value, but let's actually compute it. So we get $195, 1,000th of the time, and we get negative $5, 999 out of 1,000 times. And that gives us, well, let's see, what does that give us? Give me a second here. You compute this also at home, please. All right, so I get negative 4.8. Is that what you guys get? And again, this is negative $4.8. Okay, so that's pretty terrible, right? On average, if you were to play this like forever, it'd be like every time you played it, on average, you'd be losing $4.80. There's never, again, let's emphasize, there's never one particular game that when you play that one particular game in this lottery that you would ever lose $4.80. But I'm saying on average, right? You play this millions of times. Most of the time you're winning $5, but occasionally, every once in a while, you win $200. Anyway, so what that says is in the long run, this is what it means to play this game, right? You should go into the game expecting that on average you'll lose every time you play it, $4.80, right? And that's basically how every lottery works. Every lottery, in order to kind of make sense, has a negative expected value for those playing it, right? That's just kind of how lotteries work. The house always wins. So I think this is a great comic that I stole from somewhere. Looks like, yeah. Isn't that great? That's good. I think that's a great idea. no one really, that doesn't mean that lotteries can't be like fun still, but no one should be like, this is like a viable financial path to success for me, playing the lottery. No, that's a terrible idea. Don't do it. Okay, you could do it for fun. But. Okay, let's throw this idea out there as well. This idea of variance and standard deviation. The variance is a measure of dispersion of a random variable, and I'm afraid we're not going to say too much more about it in this course. And we wish we could be more rigorous about this, but I'm just going to throw it out there. We will say this, right? The variance is a measure of how spread out the data is, or how, and we haven't really talked about stat, but we're almost kind of like starting to talk about stat here even a little bit, right? Where are my stat people at? So the variance is given as it's the expected value of the distance values random variables are away from the mean of the distribution. And by the mean, we mean the expected value, okay? So here we're using the letter mu. It's a Greek letter mu, yay, for it to mean the mean. And so for each value, let's just kind of figure out what this says. For each value, you're computing, you're kind of computing the average. This is literally what you're computing, the average squared distance from the mean, right? So for each value, you compute the distance away it is from the mean. That's the value minus the mean. And then you square that distance so that it always gives you a positive number. And then you weight that with the probability, multiply by the probability, and then you sum up all of those distances. And that gives you something called the variance, which we sometimes denote this way and sometimes denote this way. The standard deviation is another word you've probably heard, and it is just the square root of the variance. So the square root of the variance, and it's denoted by the Greek letter sigma, which you can practice drawing, right? There are a couple of people draw it in different ways. I don't know, something like that, right? Practice drawing it. So, like I said, you don't have to know too much about it, except that we'll study it some more in statistics here. We'll actually compute it for various sets of data and things like that. But for now, you just need to know it's some measure of dispersion, and it is computed this way. Okay, so for a random variable x, let's talk about properties of these two things, and I promise we'll get back to variance and standard deviation some more in the future here. Properties of expected value and variance. For a random variable x, and if we have constants a and b, then the following hold. And these should, especially with the expected value part here, it should kind of make sense, right? If you were to shift all your data up, right? If you were to add 5 to all of your data points, right? Then the average would just be, instead of the old average, it would be the new average would be the old average plus 5, right? All your data gets shifted up by a certain amount, so does your mean or your expected value. That's what that b does, right? What about if you multiply your data by a value? Well, then actually your mean gets multiplied by that value, okay? So we might call this the linear property of the expected value, right? That this can be done to it. Pretty cool, interesting property that's worth mentioning right here and now. And then the variance has a similar property. If you shift the data up or down by an amount b, notice that that doesn't change the variance at all. And that should have, I think that has some intuition for you as well, doesn't it? Think about it. If you were to have some data that's spread out a certain amount, and then you move it up or down, just like with a translation, up or down, does that affect how spread out the data is? No, it's still the same amount of spread outness, right? Isn't it? So actually the variance doesn't depend at all on this shift of the data b. But if you multiply the data by something, that does spread it out or shrink it by some amount, and it's by an amount a squared. And that should make sense based on actually these are both not hard to prove from the actual definitions. You could go back up into this equation and you'll see why the a squared appears because of all this squaring that's happening. Okay, so work it out. You're welcome to try that if you like. Anyway, so we'll show you a way of computing that, how we might do that here in a second. Okay. Yeah, we can do this. Let's see how many more. I think we should finish this off. Let's see if we can do it. Okay. All right. Thanks for hanging with me, everybody. Let's actually do this. Let's actually compute the expected value and variance. Here we go. All right. So the value is 1, 2. This is the probability distribution we did the other day, this function. And let's actually compute the these probabilities and all this other stuff. So well, let's write these down. We wrote these down before, I think, but it would be 2 out of 62, 4 out of 62, 8 out of 62, 16 out of 62. And remember, these add up to 1, which is what they should add up to. All right, and then for each of these values, we can compute the value, 1, minus the mean. Uh-oh, we need the mean. How do we compute the mean? Well, let's do that off to the side real quick. The expected value, remember, is 1 is all these things times it's these values times these values. So it's 1 times 2 out of 62 plus 2 times 4 out of 62 plus 3 times 8 out of 62 plus 4 times 16 out of 62 plus 5 times 32 out of 62. Okay, so feel free to put this into the calculator if you like. And tell me what you get here. All right, let's see here. Okay, I've got this, and I'm also gonna so I'm getting for the mean something not real nice here, 4.1613. Whatever you get, maybe you can store that in your calculator. Okay, so this is approximately 4.1613 approximately. Does that make sense? I think that's fair. It should be kind of weighted down here more. We rarely get 1s, but we lots of times get 4 and 5s. So that should make sense. Okay, now let's return. Now we're ready. Can we call this just though temporarily? Can we call this mu? Okay, everyone's okay with that. So this minus mu, 1 minus mu squared times 2 out of 62, 2 minus mu squared times 4 out of 62. And we can compute what each of these is. 3 minus mu squared times 8 out of 62. This is terrible, right? I mean, already I'm bored of doing this. So hopefully we can use, it says down here, I kind of hinted at this. This animation came up a little early. But maybe there's a way to quicken this with our calculator. Once we've done this once and we understand the process, like I don't really feel like I need to ever do it again. All right, there we go. And if you compute these and add them up and divide by, and then you'll get the variance, right? You just add all these things up, whatever these values come out to. We'll add them up, and that will be our variance. Yay! It'll be so exciting. So I'm gonna do this on my calculator here and compute these. Like I said, did you store this value of mu? Hopefully you did. So we get bear with me for a second. I'm computing it as well. All right, so here are the approximate values, okay? 0.3224, 0.3014, 0.1740, approximately 0.00667 and 0.3631. Okay, ugh, yeah. And if we add those up, we will get approximately, here, I'll write it down here. If we add all of these up, these numbers right here, we will get the variance, sigma squared, or var of x, if you like, of 1.1675, etc. Okay, so the 3 sig figs, 1.17 for our variance, and it asks for the standard, the variance and the expected value to 3 sig figs. The expected value is 4.16. Okay, so there are 2 values, and this problem is done. Okay, so there is a way to enter this in your calculator, and it uses 1 var stats on your calculator. So if you put these values in L1 and these values in L2, and then run 1 var stats, which is available, type in 1 var stats L1, comma L2, and you do that on your calculator. Here, I'll do it too. So you put in L1, you put these values, in L2, you put these values, and then go to stat, and then go over to the calc menu, 1 var stats, L1, comma, L2, you will get you will get 4.16 for the mean. And actually, I think you'll see there, it gives you the standard deviation instead. It gives you 1.08 per sigma. Do you see that? All right, so actually, if you want that, go to your vars menu, and then go to, or actually you could take the square root of the thing we had before, and hopefully square root of the variance is this, okay? But you can go to your vars menu, and then to statistics, and then sigma, and pull that up and square it, and see if you get the thing we got. And in fact, you do. If you square this, you get this. So cool. All right. So you're welcome to use your calculator to cheat. We won't worry about this too much at this point. But we'll definitely, as we do move forward into our stat unit, we'll do some more with this. And anyway, I want you to have at least a little bit of exposure to expected value and the variance. So using the exact same PDF from the previous slide, let's compute the expected value of our random variable plus 5. That is, imagine you were someone to come along and change this data here and make this, instead of same probabilities over here, except over here you change all these numbers to be 6, 7, 8, 9, and 10 instead. Same probabilities though. What would the new expected value be? Well, it would be the same as the old expected value, right? Plus 5. So the old expected value was 4.16, right? So this will be 4.16 plus 5 is 9.16. Yay, good. All right. And then the variance will be, okay, this is a little bit of a trick question here. The variance of x plus 5. What happens if you shift the data up? The spread of the data is still the same. And so that is 1.17, I think we said, right? This plus 5 doesn't matter. It's just still the variance of x. Okay, what about expected value of 2 times x? Well, that'd be the same as the 2 times the expected value of x, which is equal to, and I'm actually going to use the full value in my calculator again here. Bear with me for a second. 8.32. I guess that's exactly what we'd expect, right? Okay. So that's 4.16 times 2. And the variance of 2 times our random variable will be not 2, but 4. The square of 2 times the variance of x. So we get, 4 times 1.17, 1.17 times 4. I'm using exact values. Hopefully you stored these in your calculator. I don't know, but I'm getting 4.67 as our answer. And then we can combine these ideas down below, right? That's all this is what we're doing here. This is 2 times the expected value plus 5, this guy. And so that will be, whatever, 8.32 plus 5, which is 13.32. and the variance will be just 2 times the, the plus 5 doesn't do anything, right? We've already said that. So this is in fact just 2 times the variance. Plus 5 doesn't do anything, and we already computed that. It's 4.67. Again, these are all approximate. Oh, this wasn't a 3 sig figs. 13.3, I guess. Right? Okay, so there we go. Now you have a very full treatment of expected value and variance. Do we want to do one more problem? Let's see if we can do it. Thank you guys so much for hanging with me. This is a long, long video. I apologize. Okay. And then we'll make this, I think, is this my last example? Yeah, and I have a bonus problem, which I won't do. I'll leave that for you. It'll be so much fun. All right, in a lottery, let's do this one problem, and then we'll be done. Whew. Here we go. Feel free to hopefully you guys have felt free to go and pause this video. All right. In a lottery, the following outcomes are possible: -5, 5, 20, and 45. With those probabilities, compute mu and sigma. All right, and by mu and sigma, we mean the mean and the standard deviation. Are you guys okay with that? Not the variance, but the standard deviation. And those, like I said, let's just use the calculator. Okay, so I'm going to actually put this into L1 and L2 on my calculator. This will be my L1 values, and this will be L2. -5, 5, 20, and 45 in L1, and 0.8, 0.1, 0.09, and 0.01 in L2. And then I'm going to run one var stats L1, L2, comma L2, and I'm just going to write this down, and I'm fine with you guys doing this too. The mean, or the expected value, is -1.25, I see from my calculator. And the standard deviation, again, I'm just reading it off my calculator, 8.7, we'll stick with 3 sig figs here, I guess, 1.79. Okay. Both of those are, by the way, the reason we might want to take the square root is because now both of these are actually measured in dollars if you want, right? The average is -1.25 dollars, $1.25, and the standard deviation is $8.79. Okay. If $2 is subtracted from the outcomes above, give the new value of mu and sigma. How much would have to be added to the outcomes to make this lottery fair? Ooh, I like that question. All right, well, let's start by answering the first piece to that, and that is what happens if we subtract 2 from all the values? Well, then the new mean is just 2 less than the old mean, -3.25. All right, and the new variance is, oh wait, it's the same as the old variance, because if you do a kind of a linear transformation of the data, a translation of the data, up or down, then the spread outness, the standard deviation doesn't change at all, okay? So this is, we're asking about the random variable x minus 2 here is what this question is asking. And so we've already kind of covered that. So how would what would it mean for this to be fair? I think we already discussed this earlier in this PowerPoint, right? This lesson. We would want the expected value to be 0. So what would we have to add to all the outcomes to make this lottery fair? And the answer to that question is, well, we know in the lottery, as it was written originally up here, that the expected value was -$1.25. So if we add to all the values in that table right here, if we add $1.25, then suddenly this is a fair lottery. Okay? If all the outcomes above are doubled, give the new value of mu and sigma. Okay, I don't have much to say about that. The new mu will be twice the old mu, which is -$2.50. And the new sigma will actually change. It'll be twice the old sigma. So, excuse me. Yeah. That's tricky. It'll be twice the old one. The variance increases by a factor of 4, right? But the standard deviation will increase by only a factor of 2. So yeah, maybe we should have said that more clearly earlier, but I think that follows nicely, right? All right. If that's confusing, let me know. 17.6 is the new value of the standard deviation if all the outcomes are doubled. Whew. Okay, thank you so much for hanging in with me all the way to the end of this PowerPoint in this lesson. We've covered like everything everything we can think about with probability here. At least the basics of, I should say, the basics of probability. I guess, you know, we have some more to talk about with probability for sure, but you've done quite a bit here. All right, so there's a bonus problem. I will leave that up for a couple seconds while you figure it out. The PowerPoint is on Edline. You can go check it out and click on this link if you want the solution, but see if you can figure it out. This is an old, can you tell? It's an old AMC problem. Yay. All right, have a great day, everybody. We will see you on the other side.